Good morning. Communication is the art of conveying meaning from one entity or a group or a person to another through the use of mutually understood signs, symbols, speech, gestures. Here in this series, The Future of Technology, presented by Harrisburg University, we have talked about conversational AI, for example, but you and I know that communication occurs through more than just speech. And today, to talk to us about intelligent systems that can interpret more than speech is Saurav Sahay of Intel Labs. Welcome, Saurav, and tell us about your work at Intel, and also please do share with us your predictions for the near term future of technologies that you are creating every day. Saurav?
Hi, Preeta. Thank you very much for the invitation. I'm very happy and delighted to be here and give a talk to the students who are watching this. So let me share my screen and start my presentation. Okay, I hope everybody can see my screen now. So I am a tech lead and a senior scientist at Anticipatory Computing Lab in Intel Labs. I lead the area of multimodal natural language interactions in my department. I'll be talking about multimodal intelligent systems. Before I do that, let me give a brief background about myself. I hail from the state of Bihar and from the city of Patna. And like every other student and parent of the student back in the days, maybe it's true even now. My dream was to get into the prestigious Indian Institute of Technologies in India. Unfortunately, that dream, or fortunately, I would say, that dream didn't come true. And I got into another interesting competitive program called Bachelor of Information Technology at University of Delhi. And my story starts from there. So during when I moved to Delhi, I was fortunate enough to see around lots of interesting research institutions in and around my college. I worked at Jawaharlal Nehru University at the Bioinformatics Center while I was a student at the University of Delhi, and I spent a very good 1 year over there. And I had a great PhD student who was my mentor, and together we developed a Markov model library, and that was a very good point in my career where I got introduced to research methods, worked on something very interesting, and I applied to various PhD programs in US, and got into the program at Georgia Tech. I got into the database group where we were trying to do text analytics. There was a project for for Disease and Control that I was working on initially, and from there, basically, I did an internship, first internship in 2005 at IBM Research, did another internship in 2006 again at IBM Research, and slowly started moving from pure text analytics type of projects to more natural language understanding and natural language processing type of projects. And I made a transition from the bioinformatics program to the computer science program in 2007 at Georgia Tech, and moved to the cognitive computing lab. And worked on this project called Cobot, which was my thesis project. And Cobot stood for conversational bots or community bots or um, yeah. And then in 2010, I also worked at IBM on the IBM Watson project that I'll briefly talk about at TJ Watson. In Later during the end of my uh, grad school, we incorporated a company along with my advisor and another colleague, another student at Georgia Tech, and we did the startup for a little over a year. And I think, I mean, personally, I was not mature enough to understand the implications of a startup. We couldn't sustain it for long. Graduated from Georgia Tech. Then we went to then I started working in Princeton at Siemens Corporate Research Lab. I worked on healthcare decision support systems over there, and around October 2012, I moved to Intel Labs here in Bay Area in California, and have been happily working on various facets of language understanding, multimodal systems and applications that I'll be talking about, and also recently working on a lot of deep learning related projects. So just one slide about my thesis work, which was the Cobot project. So in Cobot, what we basically built uh, a community and a platform for people to engage in conversations about their healthcare information needs. So Cobot was basically a technology platform that could parse text, that could understand the medical meaning of text, that could help connect relevant people together using the recommendation technology. It would use a lot of natural language processing, machine learning classification, recommendation technology, and a real-time community platform for supporting this community bot infrastructure. So it was a project that I'm still extremely proud of, and this is what I started doing at Georgia Tech, and from there into 2010, I worked on this IBM Watson project. Mm, which was the famous project that won at the Jeopardy competition, and it's really a milestone in the history of AI and AI technology, that they built such an interesting, complicated system that could parse extremely complex questions and compete with champions, and actually defeat champions. So this was a very complex pipeline that took a question, decomposed the question, figured out lots of answer candidates for the question, then again looked at millions of evidence repositories, books, knowledge bases, knowledge graphs. It did a complex evidence retrieval and scoring against the candidate answers that it had generated through multiple parallel paths, and synthesized all the information, applied machine learning, modeling, and scoring techniques in the end to come up with answer and confidence. And back then, they didn't use any deep learning technology, but they really built an extremely competitive system uh, back then. So so at Anticipatory Computing Lab here at Intel, I work on um, many interesting projects, primarily around sensing and sense making. So we have systems that can sense what we are, say, for example, writing on our devices, look at our calendars and location information, our emails, and compose all of these all this information for various interesting applications, like recommending something to someone at the right time at the right place. We also work on interaction projects. The diagram that you see at the top middle is, I'll talk about that briefly, is a system where we have built a platform where kids can interact with this agent that we project in the house. This project is called Kidspace. Then on the top right, we're showing some affective sensing technologies we have built to develop emotion sensing, sentiment analysis type of work. We do heart rate, like physiology monitoring, your text monitoring, your voice analysis and monitoring, for doing all sorts of interesting prediction of your longitudinal emotion and affect states. Um, so so let me go into the the meat of the talk, the multimodal research that I'll describe here. So mainly multi all of natural language, natural communication. Humans, the way humans communicate is always multimodally. We the meaning that comes out of our mouth also contains voice, is several times entangled with gestures, and it has many modalities. We use language, we use vision, we use various intonations and sounds for conveying signals. Our physiology changes while we are communicating, and there are many other modalities that we can leverage for this human machine human interaction system. So it's not just a one way interaction between a human and a machine, but how a machine can interpret the human's actions and then process that to again communicate with the same human or another human in interesting ways. So I'll just show a brief video of this interesting mm, um, um, effect called McGurk effect that was discovered, I think, in 1970s. Where let me play this clip first. It So what is happening here is that this person is uttering a sound, and he uttered that sound 4 times. And so what they experimented was that they mixed the sound with different images. So the first one sounds like a ba. The second one, in the second one, the person actually, it to me it sounds like va. But actually, what in all these different sounds, they're using the same clip. They're just repeating the same clip in a cycle. But since our perception is so entangled with our auditory system that we perceive the sounds as different sounds, although they're the same sound, because of this effect of perception playing along with the auditory signal. Similarly, I mean, gestures are thoughts and actions. A lot of people are more use more gestures, and they can actually just communicate through gestures many a times. So what I'm trying to say here is that this our natural interaction is always multimodal. We use these entangled signals coming through different modalities all the time, and current technologies primarily look at unimodal. Say conversational AI is primarily about text or voice based interaction. Then they're not currently leveraging other signals appropriately. So there's a lot of scope for bringing together these multimodal signals together to create more interactive, affective systems for human machine human interaction. So natural these natural communication modalities I'll be talking about like verbal, visual, and vocal. These are how we use words, or how we form our sentences, or what kind of tone and voice quality and vocal expressions we use in our communication. The gestures, body language, eye contact, all of these basically change our communication tremendously. So what are the interesting applications of these multimodal research? So now we are starting to see some projects along even commercial projects along social robots. So this is a robot called Sophia by a company in Hong Kong that also can actually produce many facial expressions and talk. When you talk to this robot, it would seem like you're talking to a real person. It's so natural because of the facial expressions. There are there are immersive games now that a lot of you have played with the Kinect sensors. They are becoming so immersive and so interesting now that you can really feel like you're actually in the game while you're playing certain immersive games here. more interesting personally to me are applications around trying to impact or improve the mental health of a lot of people who are going through stress, panic attacks, anxiety, phobia. So we can develop these monitoring systems that can look at say people's heart rate, skin conductance, the blood flow, the way they speak, their pupil sizes, and a lot of these signals that we can monitor to understand whether a person is going through certain mental health crisis or mental health situation or not, and hopefully intervene appropriately for these kinds of issues. Another very interesting and commercially relevant application area is the space of e-learning. So now there are schools in Bay Area and all over that are trying to bring in technology to monitor the engagement of students, and how they are learning various concepts, and how they are generally learning socially in the environment, and use all of these to improve or guide the teacher to create personalized models for each individual student, and how they should improve their learning ability. So a lot of the this applications, and the thing that I'm going to talk about is in very early stages of research. There isn't a whole lot of concrete commercial application today, but in the next few years, I'm pretty sure we'll start seeing a lot of very interesting multimodal applications on all of these areas. So so again, to briefly go over some of the particular research applications that are interesting, are things like that use vision, speech, and dialogue modalities, are things like emotion understanding, where you can see this is Ekman's emotion states, detecting happiness, surprise, sadness, disgust, anger, contempt, all of these emotion states. If we can detect through a combination of someone's voice, speech, vision, and text together. I'll particularly be talking about one of the technologies we have built for this multimodal emotion recognition. There are other very interesting work happening where now chatbots are being developed that can persuade people for certain kinds of activity. For example, donating to charity. So I've seen some papers and some work. Actually, we are funding at some academic university to work on these persuasive chatbot technology for social good. So there are engagement related projects I talked about, and also in interaction. There is a lot of interesting work happening where people are leveraging the camera to see around the look at the environment and be able to understand or interpret what's going on, say generate caption about the scene, or even engage into some kind of a dialogue about the environment. And I'll also be very briefly touching upon a project that we recently did for scene aware dialogue. There are other very interesting application areas that I've mentioned over here. So now I'll briefly talk about three different projects at a very high level. First one is this emotion understanding. The second one would be that multimodal scene aware dialogue, where you can do a dialogue about the perception in the environment. And the third one would be something around math learning or math tutoring, development of this math learning technology for kids particularly. So I'll briefly go over these three projects. So this multimodal emotion understanding is you can think of this as a sequence classification problem. So generally our emotion states are temporal. They don't change drastically. It's a time series of signals that is continuously coming along, and you need to classify the instances of these sequences into various emotion states that are the output states of classification. Generally, the state of the art accuracy for a lot of the data sets is around 80% using the latest deep learning technologies that exist today. Still, there is a serious dearth in real world data sets. Therefore, we don't see a lot of real world deployment of this affective technology today. Most of the data sets are toy data sets that have been developed by some academic labs, collected through channels like YouTube and other like, or enacted in studios, and these data sets are currently being used. But a lot of work is happening for in the wild understanding of emotions also at some places. So an example that I'll try to motivate you all to appreciate the value of multimodal signal. So this is me. Imagine I'm sitting in, and I get an email that says with the subject urgent performance review, something like that, from my boss. So this, what how should I react to this? I should probably this would could probably mean something as a fear or a surprise or some kind of a negative emotion in my mind. But looking at other things like what am I doing, what's my heart rate, what's the audio background, and my facial expression, this entire multimodality of the signal uh, can can really help resolve the ambiguity and help improve the confidence of predictions that the model has to learn. So basically, this is the motivation. Going, why do we need to go from unimodal analysis to multimodal analysis? It primarily can help resolve ambiguities in a lot of situations. So I'll briefly give a very high level overview of general principle of neural networks here. So in a neural network, you have you represent your input, which is your raw signal, can be your text signal or audio signal or video feature signal. You in some way represent these input representations and connect it through a series of different kinds of layers. These could be fully connected neurons. These could be more like fancy uh, nodes, like say a recurrent network or a convolutional network, and you pass the input through a series of hidden layers, which you decide through various experiments, and then you have an output which basically gives you the output class. In the previous case, it would be, say, surprise, for example. Given my email, my face expressions, my heart rate, the output should be surprise for that particular instance. So at the output, you define your learning objective, and then you try to learn a model through back propagation algorithm on this neural network. So primarily at a very high level, the fancier networks are also some simple variation of this standard architecture of input to output with a lot of hidden layers in between the input and output. And uh, mm, and and on the right, I show how, say, for example, if you have multiple modalities, you can represent the multiple signals separately in the neural network, and then have some kind of a joint representation. And also nowadays, you can with some very nice algorithms, you can try to reconstruct your various audio and video representations. There's a lot of very interesting blogs and Coursera, Andrew Ng's class, and several other interesting resources online that you can look at if you're interested in this topic. But It's not rocket science. So so text, so I'll very briefly talk about this representation of text, audio, and video, and how we create a neural network to develop a technology for emotion recognition. And so we I'm talking about this project that we did, and we actually participated in a challenge in at a conference called Association of Computational Linguistics, ACL, this year in 2018. And the model that we developed here came got the first place in the sentiment analysis track, and the second place in the emotion analysis track. So this is a fairly state of the art model for emotion and sentiment recognition for multimodal emotion understanding. So, and I'm not talking about a lot of details. I'll keep this at a high level. I have a reference here. You can Google that reference, and you can read the paper if you're interested in knowing more about this particular work. So you represent every input signal. So here in neural networks, we represent text signal as a series of n-dimensional vectors. So there is a very interesting technology first developed by Google called word-to-vec algorithm, where they came up with the first algorithm to represent text as a composition of all the text that are there. It's an unsupervised learning, very beautiful algorithm that can help represent text as a vector of features. This has been, I think, in my opinion, one of the biggest contributions in text analysis work in neural networks. And now, after the word-to-vec algorithm, people came up with much more fancy algorithms and very interesting techniques. The one here on the right is called contextualized word representations, or ELMO, that was recently developed by Allen Institute of AI. And we used all of these models in our work for representing text. Um, so also, a lot of the work in deep neural networks, they try to represent raw signal and learn a model directly from the raw signal. We also augmented our raw signal with external knowledge. So we tried to use lots of lexicons that people have developed in the psychology domain to learn about sentiments and emotions, like words that have certain orientations of emotions and sentiments. We used that knowledge and augmented it into the raw signal in our neural network. And we used some published work and algorithms to augment our text knowledge. Similarly, for audio signal representation, we basically uh, improved the standard pipeline of I vector training. I vector is again some vectors that we generate in the process of audio signal representation. We improve that vector generation by making it phoneme aware. So for sentiment and emotion, we believe that phonemes give a lot of signal for detecting your tone, generally your arousal level, and your valence, primarily your arousal in the voice, in the tone, can be determined heavily by phoneme. So we developed this phoneme aware I vector pipeline for representing the audio signals. Um, for video representation, we used CMU technology. It's called OpenFace. CMU has developed a very nice library called OpenFace. We used OpenFace to detect various facial landmarks, head pose, gaze. These are called facial action units, and they also help in determining your emotion pretty nicely. They contribute greatly to determining the right emotion. So So the model that we developed for that a lot of people had not thought about was how to leverage both the entire temporal information. So this model was initially developed for detecting emotion in videos, and these videos are long temporal sequence of frames, and each frame generally people try to develop a model that takes a frame and only looks at the frame and determines the emotion or sentiment for the frame. We developed a temporal model that looked at the entire sequence of frames in the video, as well as how, say, one a particular frame in one modality could be influenced by some other frame in the other modality, not just at that particular time at that moment of time, but may across the moment of time. There is research where say gesture follows voice, or certain expressions are not time synchronized in our action. So for to leverage that kind of intra cross modal dynamics within signals, we use that to create our model that could capture all these intramodal and cross modal dynamics of the signal. So I'll not go into the details of this model, but we developed a relational model called relational tensor network, which is basically a neural network which is composed of several layers of LSTMs, which is a kind of a recurrent neural network model, and it generates these various activations and fuses the information from the audio, text, and the video signal through a process of tensor fusion, which is that this part that you see over here. This tensor fusion operation helps capture the cross modal dynamics, which whereas a lot of work simply concatenates the text, audio, and video representation together, so that it cannot leverage the cross dynamics between these signals. So we created this model, again building up on a lot of existing work that the research community has already done, and we showed that some good results based compared to many state of the art algorithms and baselines. And this is the paper that I reference here: multimodal relational tensor network for sentiment and emotion classification. So this was the technology for that emotion recognition. Using deep neural networks, and how we use the multimodal information from audio, video, and text channels to create a system. Now this system was basically used or developed for looking at videos, but the same technology can be applied to look at to basically use the camera to look at the world or environment around you, and use that information as, say, a video, a live video that's happening, and then detect the same emotion and sentiment from how I am talking. And it could basically be running live right now, and help me look at how my emotion and sentiments are changing while I'm giving a talk, for example. It could also be used to look at you guys who are watching me talk, and see see your emotions and how you react to how I'm talking. So there are some interesting applications of this technology. The other project that I'll quickly talk about is this visual dialogue. So visual dialogue is this very new area of research, where the goal of this work is to help create these interactive chat bot that can also see the environment around you. So you can ask questions to this chatbot that okay, how many people on wheelchair, given this image or a video that's playing, you can ask questions, and this agent can look at, can see the video just like we see the video, and try to answer questions about the video. How many people on the wheelchair? What gender are the people in wheelchair? Which one is holding the racket? Is the other one holding anything? And it's really fascinating to see how these technologies are now being modeled on some data set, and they work very well uh, on other test data sets, or real other data sets. They can do counting very well. They can detect the objects pretty nicely. They can generate simple answers to questions. Although this, again, I'll say that this technology is at a very early stage of research. It's way behind say the complex Watson technology that can parse complex questions. And in the world of, like, it can answer very complex questions. This visual dialogue technology is nowhere near that, but a lot of people are working to improve the state of the art for understanding and having more engaging and interesting conversations about videos with this in this technology. So the framework of this task is like, there's a image, there's a history of human dialogue, which is these episodes of questions and answers, and a current question or a follow-up question. And the task is to produce a free form natural language answer about this question. So this visual why is this task interesting? It really relates language to the world. And it's an open set and open question answer, like technology, unlike other AI problems like chess, for example. um, Again, this is a step towards uh, being able to learn visually. So I mean, most things an agent needs to know aren't written down, and are grounded in real world experiences. So if we have a technology that could watch things and learn, then we leave it out, and it's going to learn a lot of interesting things, just like a child learns in left out in the environment. So so there's a lot of promise about this technology. Again, this is very, very nascent. Best performance systems perform reasonably well on standard images they have been trained on. And there is, again, a lot of this there are toy problems only. Currently there's a lack of lots of data sets to train more interesting models. Again, these can answer simple obvious questions. Okay, how, like, for example, how many people do you see? Okay, I mean, why would I even query a bot when I see that there are two people? Certainly, I mean, there are certain niche use cases. For example, this could be useful for a blind person, for example, or this could be useful for a surveillance agent who has deployed a robot in an emergency situation where the person cannot be, and it is querying the robot to ask questions, and the robot is answering back to the person. So there are some interesting use cases of these simple applications. But again, I mean, if these technology could include deep reasoning and common sense understanding, a lot of more interesting things would happen, and they are actually happening. The standard pipeline of this system is some kind of an encoder decoder architecture. It's a deep learning model, the fancy word being encoder decoder architecture, where you basically take the video, you represent the video, you take the question or text, you represent the text. So this part is the encoder part. You encode the input, and then you have to generate the answer. So this part is the decoder part. And there are standard deep learning technologies like CNNs and RNNs that are used for this encoder decoder pipeline. So we built a model um, which looks like this. I'll not go over the details, but we submitted this work at this AAAI conference in early in 2019. This work got accepted at the dialogue state tracking workshop at the AAAI conference, where we basically used the similar idea of encoder decoder, and we did many experiments about trying to improve the question representation by use of topic models, by use of attention in many interesting ways. How can the question attend over the dialogue history to figure out the answers more appropriately? So we basically did a bunch of experiments on a standard encoder decoder architecture to see if we can improve the answer generation using these experiments, and we showed some improvement. For example, so given a particular video, if the question is there sound to the video, and the ground truth answer is yes, there is sound, nothing important, our model could correctly decipher, yeah, yes, there is sound in the video, unlike the baseline model where which would fail in certain situations. We um, we we did experiments for representation for the attention. We try to look at how the attention mechanism that we have incorporated improves the baseline, and we saw good improvement. And similarly for our topic model based experiments, we also saw some improvement compared to the baseline with our changes to the standard architecture. So now I'll very briefly talk about this very interesting project called learning oriented, uh, like basically learning in smart environments or interactive environments. Um, so this is a project called KidSpace, and we published this paper at ICMI this year, and the the goal here is to create a smart space that and use these characters, interactive characters, to engage the children uh, in playful, immersive, learning based interactions. So for example, on the right you see this teddy bear who is asking questions to the children, like how many birds do you see, or it could, on this left hand side top frame, you see this teddy bear can actually jump from that table to this another shelf in the room. So how we do this is through creating a 3D model of the real world environment and mapping it into a virtual world. We using Unity 3D for our modeling, and then once we have the model of the real world in the virtual world, we can deploy it back in the real world through projection technology. So we use several types of projectors to bring back the characters projected in the real space, and now these virtual characters have a sense of or have knowledge about the things in the room. Where are the tables, where are the chairs, where are shelves? So this teddy bear can can basically ask can determine that, okay, that shelf is too far, I cannot probably jump. So can ask the kid to help the teddy bear move from that table to the shelf. So we're trying to experiment and explore many interesting applications of this kind of a space for interactive dialogue. So this year we did some work around trying to create a math learning or math tutoring agent, which is again multimodal. We had a very good intern who worked with us on the project this year, and he's also joining us full time soon. So basically, this project is about it's called reference resolution. So you show a bunch of images or objects like this to children, and you can ask questions. Like add all the things that you see in the night sky. Um so and you randomly generate these images. You can ask, like, okay, how many purple objects are there, how many cats are there, how many, if you remove one cat, how many cats remain, how many polygons are there. So you could ask anything given a particular image, and then the task is to create this bot that can that can engage with a child in free form dialogue and entertain the kid, to ultimately with the goal of trying to teach the kid these concepts about simple counting, addition, subtraction. And um, this is a very interesting but complex problem that requires a lot of data collection, annotation, bootstrapping through a two-party system, real-time data collection system, and then training models, deploying the models, iterating. And it's fascinating how these interactive multimodal bots are being developed now. So this is a work in progress, and we are actively pursuing the goal of trying to create this interesting learning system for kids. And I would like to now just close giving a short short summary and high level thoughts that I feel. So today there's a lot of hype about AI. We see articles about AI taking over humanity and things like that. All this is like not true, but still, the promise of all of these newer approaches. And marrying them with the older approaches, the promise is real, and there's a lot of progress happening today. And then there are many interesting real world problems to be solved. um, and there's a huge dearth of talent. Even being in Bay Area, I know how hard it is to get good people to work on these problems, and a lot of people would resonate my thoughts here. I would also like to add that this might look complex, but none of this is rocket science. It's just a combination of a lot of time, and the colloquial phrase, you have to burn that night lamp, dedication, and the right direction, and a lot of exploration. Basically, you have to download code and run it to see how many projects happen, and then you learn through practice, through exploration. I would like to add that continue being a dreamer. I and you have to always uh, do that. I mean, it's you can never stop dreaming. If you stop dreaming, you can not progress further. And it's always you have to take the baby steps first. Nobody becomes as famous as like, I would not call out names, but there are famous researchers, scientists. They all have gone through phases where they started with baby steps, and then be where they are today. And only if you're passionate about it, I mean, go for it. Nothing's stopping you. There's many failures are the best things that can happen to someone. I told you guys very initially that I couldn't get into a prestigious institution when after my high school. That was a first failure that I saw. I have seen a lot of other failures in the process, but it's the best thing that can happen to you in the learning process, is to fail and then again try try to continue doing what you're doing. So with this, thank you very much. I would like to switch to Preeta. Thank you very much, Preeta, for this time here. Let me switch over.
Thank you. Thank you. Thank you. So, Sarah, congratulations on that award. I think there were two awards that I counted. So, really impressive work that you've been doing. And I just love the project with kids. I can see there's so much that needs to happen. But most of all, thank you for that advice you gave. It was very inspiring and encouraging. And I think a lot of people, young people, would really appreciate that. So, once again, thanks again, Saurabh. Um, and
My,
again, yeah, go ahead.
my pleasure. Yeah, thank you very much for this nice opportunity to talk to folks back in India. So yeah, feel free to ping me if anybody has questions, and I'll be happy to answer.
Absolutely. And thanks again. Thank you, everybody. Good evening. And once again, thank you for your time and attention. Goodbye.